actually only one more lecture, and then I'm going to give like a recap and some very brief gists of possible interpretations of quantum mechanics. But first, we have Jalan talking about reference frames, and that'll be the first half. Record it. Take it away. Okay, hello. My name's Jalan Ziyad. And today, I want to argue that we can use reference frames to learn a little something about the foundations of quantum mechanics. You may be already familiar with, concepts of reference frames, but I would argue that its consequences for the interpretation of quantum mechanics aren't often explored, and that we could potentially learn something interesting if we shift to another perspective. But so how do how should I on the screen? Yeah. Okay. So I want to consider this question: does the quantum state mean anything by itself? Just simply a vector in Hilbert space. Equivalent is the entire universe describable by quantum mechanics, or is the universe a computer? I will say that the answer to this is potentially no, in light of these two types of information. Asher Paris and Scudo distinguish between speakable and unspeakable information. Speakable is information where the choice of representation does not matter. So these are our bits and our qubits. You can equivalently represent them in two levels of an atom, two levels of a spin half system, or any two-level quantum system. And bits, you can represent them in two voltage levels, a digit on a piece of paper. You can convert one to the other, and they're all equivalent representations. On the other hand, you have unspeakable information where the choice of representation does matter. These are like directions in space, and there's no way to communicate a direction in space without pointing or referring to a landmark or giving a physical system that is like aligned in that direction. So there's no way to convert unspeakable information to speakable information. And this unspeakable information is basically a reference frame. We have defined our states relative to directions in space or points in time, phases. And that quantum information doesn't just sort of exist out in space. Yes.
I have a question. So suppose you have a spin.
Yes.
A spin, right? The levels are degenerate unless you apply a magnetic field, right? That decides the direction, right?
Yeah.
Puts a direction in there. Do you mean the spin states created by this direction or before this magnetic field is applied?
By the magnetic.
After the magnetic field
after the magnetic field is applied.
So wouldn't that make it unspeakable because you have to apply a magnetic field to something?
Well, you can define one of the states. You can define two orthogonal states, and you define one as 0 and 1. And any choice of, basis is an equivalent way to represent a qubit.
Oh, I just, yeah. Okay.
Yeah. That's basically it. And so in this talk, I'm going to cover, I basically want to demonstrate that reference frames have consequences for our interpretations of physical theories. And so the answer to this question is the universe, quantum computer, described fully just by the quantum state. I will say not likely, and I'm going to use an argument by Ben Schumacher called the quantum Grue-Bleen problem. The quantum Grue-Bleen problem to argue this. And I also want to show you how reference frames are intimately connected to decoherence. We always define a state relative to a reference frame, and so lacking information about that reference frame actually limits our ability to compare the two operations.
I thought you said qubits are speakable, so we don't have any reference frame attached to it. But what do you mean by states are defined with respect to a reference frame?
So it's speakable in that like a logical zero is a logical zero in physical system. But you actually have to pick like a certain physical system to represent the logical zero. So you have to have a logical zero relative to like a certain reference. So you define speakable information relative to a reference. This also leads to the task of aligning reference frames, which is related to calibration. So let's dive into quantum Grue-Bleen problem. Basically, Schumacher was arguing against the many worlds theory and this maxim of Price-DeWitt that the mathematical formalism of quantum theory is capable of using its own interpretation. And so many worlds assumes that the universe is representable by a single wave function that evolves with time, and that no wave function collapse happens. And so how are measurements thought in this theory? Well, a quantum system, a measurement device, and the state of an observer's mind are all described by quantum mechanics. And before measurement, they are uncorrelated, but measurement sort of correlates all three subsystems. And you can track this measurement by looking at observables, which track correlations between the mental state of the person and the measurement device. So when it's 0, no measurement happens, and when it's 1, a measurement occurs. And so you just need wave function for the universe and these observables, and that gives you like a picture of what's going on. Schumacher argues against this by considering two universes, one complex, one simple, that have the same dimension of Hilbert space. Both are able to be described by different time evolutions of the same initial state. And using this fact, you can actually convert any observables in one picture to time-dependent observables in the other picture. And so any sort of statement you can make about one world using these time-dependent observables, you can make the same statement in the simple world. And so it seems like just the mathematical formalism by itself is not enough to distinguish a very complex world from a very simple.
Just a little comment. If mathematicians would not say Hilbert space is determined as a lot of the inner product.
Completeness.
Yeah, completeness is the point.
Okay, yeah, that's not exactly a precise statement. There's a reason why I didn't say that out loud. But so to argue this, he sort of comes up with this reversible theory schema to make this applicable to more than just quantum mechanics. And so this considers a set of allowed states, a group of kinematically allowed maps, which are assumed to be reversible, and a set of similarities with property S. Each similarity is a bijection, so it can be convertible, and that when applying the similarity by conjugation on a kinematic map, you get another kinematic map. And this is a way, so applying a similarity converts one description to an equivalent description. And we can see that all kinematically allowed transformations are also allowed symmetries. And so he also defines instances and interpretations within this theory. An instance of the theory is just an initial state in a sequence of kinematic maps. And an interpretation is just a proposition that depends only on an instance of the theory. So the truth value depends only on the instance of the theory. the property of the reversible theory should be that if you transform to an equivalent picture using a similarity transformation, the true value of that proposition shouldn't change. And so any instance that is equivalent to another by similarity transformation should have equivalent true values for a given proposition. So if the set of kinematic maps is transitive, meaning there's any for any two states, there is a kinematic map that maps one state to the other. Then the theory actually has no state-dependent interpretation of propositions if we assume this this property. And so Schumacher says that this sort of property that each picture is equivalent to the other, that's akin to the DeWitt maximum. And so if we assume the DeWitt maximum that everything is, describable by this reversible theory and nothing external to it, then our theory actually says no meaningful statements. And so there must be something else that we attach to this theory, something outside, to give us meaningful interpretation. So, for the example of quantum mechanics, this is like, a partitioning of the Hilbert space into subsystems, or equating a direction in Hilbert space with a measurement device, something. There must be something else that we attach to that quantum state. This framework is general enough that it actually applies to classical physics. And so, what can you say about classical physics and of this quantum thing? Turns out that this was actually reference frame problems were actually considered way back with Descartes, Newton, and Leibniz. So Descartes, the creator of Cartesian coordinates, was trying to look at the relativity of motion, but he didn't take into account inertial effects, and had some counterintuitive ideas about this. And so Newton and Leibniz sort of developed their own separate treatment of reference frames. Newton just assumed a fixed background reference frame, because if you don't assume a fixed background reference frame, then you can only talk about relational quantities, and you can't talk about individual systems. Leibniz just rolled with the relational quantities and assumed only they exist. And so you can never treat physical systems as separate. All causal relations are just apparent and reflective of the order of the universe. He had some sort of freaky ideas about the world. Yes.
Why do you need a fixed background reference frame to talk about individuals? I don't believe in any fixed special background frame, but I'm talking about this water bottle right now. I'm not talking about the table. What's wrong?
So if we went on get into sort of getting a little short on time, but you can actually look at bonus slides. Sorry. Yeah.
Very briefly, how do monads come into this?
Monads. We're really not gonna go into monads. It's a little too.
Could we stare at one?
Let's go back to Newton. I think the physics world back in the day collectively got behind Newton's physics. So I guess this comes with this definition of place and motion, and basically you think of the momentum of an object as the sum its parts, and so to determine and this motion is relative to like some place that the object is in. And so if you define that motion relative to its place, and that place is moving, you also have to define the place's motion with reference to the place that the place.
But you only have to define motion in your reference frame, doesn't have to be related to anything else except your choice of reference frame.
But you're like, you're already like assuming that there exists like a fixed reference frame.
No,
You're already-
None of them are special. You talk about the motion relative to any reference frame, and none of those. frames
But
are
there are actually like non inertial reference frames.
Yeah, I mean, the inertial
So,
ones are
like,
special.
fictitious.
Yeah,
But how would you define special from not special if you don't like assume?
like frames where F equals NA holds. Like those are the special ones.
But
like
that's also
That's all.
defined in terms of the reference kind of circuit.
Yeah,
F is equal to ME is defined with respect to a reference frame.
Yeah. And in some
yeah, there's like
reference
fictitious
frames,
force doing.
We shouldn't discuss class with the plot.
Well, anyway, it's becomes way simpler if you like just assume that it's like a background reference frame. Okay. Yeah. And so that kind of concludes our interpretational sort of overview of reference frames. If we move to a more operational picture, where you consider Alice and Bob and spin half part. And so let's assume that Alice and Bob are just floating off in space. And Alice wants to communicate the state of the spin half particle to Bob, but they don't share the same reference frame. They each have their own reference frame. Well, when Alice sends that state to Bob, what is the state that Bob should assign that particle with respect to its reference frame? Well, if the relationship between Alice and Bob's reference frame is known, then Bob can just apply the transformation to his reference frame to and then adopt the state that Alice applies to her. Adopt the state that Alice writes down for her. But if it's completely unknown, then Bob has no choice but to average over every possible orientation of that spin path part and write down a mixed state. And so you can see just from this example that lagging the reference frame leads to a type of decoherence. One way they can get around this is if Alice has like a gyroscope that is like aligned with her z-axis and sends it to Bob, and Bob's able to do measurements on that gyroscope and align its reference frame with the gyroscope, and then they're able to send particles back and forth without any sort of interference. You can treat this actually group theoretically. If we have H Hilbert space, you can represent a reference frame transformation with group. So we assume that this is like a compact group, and assuming that it's a finite or Lie group. For example, for 3D rotations, the group is SU3 or SO3. We have SU2 and U1 for phases, and even think of like polygon frame as the type of reference. This assumption of compactness lets us define a hard measure, which acts on H unitary representation of via unitary representation, and this allows us to like consistently define like averages, so like transformations. And so, if the relationship between two reference frames are known, then you just apply unitary representation of that transformation. And if it's completely unknown, that leads to this G twirling operation, where we sort of like integrate over all possible transformations. And this leaves the state as a mixture of like states in subspaces that are like invariant to these reference frame transformations. And so this sort of forbids like the creation of coherence between like these different invariant subspaces, which is called a superselection context of particle physics. And this is the relationship between a superselection rule and reference frames first sort of explored by like Aronov and Susskind back in the 60s.
Why does Susskind get his picture, but not Hart?
Because I do.
Because you know, you don't know who. We have a hard enough bone back there.
Yeah, I should have put Aronov. Yeah. You know, in hindsight,
Still writing papers at 93.
very impressive. And so let's look at an example. This is just phase reference in optics. And so you can write down the weird space and the basic states or eigenstates of these like number operators, which are like the number of excitations in the mode. And the phase operator is like carry representation. One, and you can sort of decompose this operation into like some operations on this like number subspaces with constant like excitation, total excitation number. And so if you have like two phase references that are like completely unknown relative to each other, then you do this like twirling operation over all the phase transformations, and this gives you a mixed state where you like basically decohere all the coherence between different number sectors.
Maybe I'm just confusing myself. So, from what I understand, right?
Yeah.
What you're saying is, if I don't know if you're sending me a particle and we do not know, so I do not know your reference frame, and all I can say is, so I do not know what is the exact state, so I'm gonna call it a mixed state. I'm gonna average over all the reference frame. That is the point you're making, right?
So that's not the only thing. If you have like some other information, please that it's it's more likely to be certain transformations over others, then you don't necessarily have to apply the uniform average.
Sure. But my point is, assuming I have no information for it.
Yeah.
And you keep sending me the particle negative. Why can't I do something like a tomography and just figure out what the state is then?
You're figuring out what the state is.
You never learn the reference.
With respect to
Oh,
what
yeah, you
happens,
never learn
right?
that ref, but you still have to reference top, like.
How do you know what measurement you're doing?
You don't know whether you're doing X, Y, or Z measurement.
Sure, but it doesn't really matter. Like
It does,
It does.
because
So you did
you're thinking, you have to say, if you're going to say, if I get a 1, that's 1 along Z.
Yeah.
You have no idea, that's not what he called Z.
So your topography would give you control thing, won't the.
right. Oh,
You don't know, well, yeah.
oh, so it will tell me what the state is in my reference frame, but it will not.
Well, it would tell you this ignorant average one instead of.
Assuming that, yeah, like, I guess you're also assuming that it's like according to slope.
I mean, this is like a solution to this. Can't Alice just also send a reference frame in the sense that she'd send like, okay, I'm gonna send a bunch of spins along what I call the x-axis and the y v now. Now they're all on the same page about the reference frame. Like, isn't that the easy solution to this problem?
Yeah, so that's actually what we're gonna get to.
Okay, sorry.
Before we run out of time.
It's like synchronizing your clocks.
Yeah, synchronizing clocks, it's all the umbrella term for that sort of task is called the lighting. Reference range.
Hey, Jay, sorry to keep going.
Yeah.
I didn't get the point of this slide. So you have so you're defining some K modes of an electric field. If you're defining it, don't you already need to have a phase reference to define the K modes?
Yes, but if you're giving it to another party, different reference, it's like coordinated.
Alice might use that reference frame where Alice knows the phase, but once she sends it to Bob, Bob has no idea maybe what the phase is because maybe Bob doesn't know their distance quite well enough. So Bob has to do that sort of averaging. But yeah, Alice, whoever the preparer of the state, I think knows.
Okay, so the Bob only knows that there are photons in K mode, right? But they don't know which K modes are with respect to which reference.
Or they don't know what the phases are, right?
They just know the number stated phase vector.
Yeah.
Like it doesn't have phase.
Okay, yeah,
Got roughly 5 minutes.
That's important.
Okay. So. Yeah, so this is another example with spin half particle in a magnetic field. If we apply like Rob using oscillating magnetic field, then that sort of oscillation serves as like a phase reference for that state, that particle. And that's related by an element of U. And so, do we have time for this?
You can just take time away from the road,
Yeah, let me draw this up.
It's the last lecture, I think we can.
Okay. So this has a nice picture. So let's draw a black sphere. Let's have a spin. It's defined relative to some stationary magnetic field, which defines its direction. And then we have some, I guess, transverse field, which leads to, wait, hold on. First of all, let's consider that this is undergoing precession of this axis. And in order to make this, stationary, we sort of like go to the rotating frame. And then we apply, an oscillating field with frequency omega. It has a clockwise component going in the rotating frames, giving out frequency omega plus omega naught. And then you have like a clockwise component, which is going after difference between those two frequencies. Rotating wave approximation ignores this, but I guess the operation, the rotation that we do on the block sphere is sort of these frequencies. If this frequency is, fluctuating in time from one time step to the other, then this actually leads to decoherence or dephasing, because we can't pick out what the phase of our spin is, and so it sort of, randomly moves away from where we think it is, And the average of all of those sort of random fluctuations sort of like average out to zero. So that sort of like squeezes the block sphere to like a lot. So like perfect lack of like phase information in that case leads to like complete phase. That's like a twirl over rotations of the block sphere on its axis. But if there's like some correlations in time, this could lead to a finite rate of phasing or a non-Markov. So the phasing and non-Markovianity actually are sort of like reference frame derived. And this is actually like used practically in calibration and phase estimation. One possible way get around it's like sort of super selection rules is encoding your state in one of these like invariant subspaces. So like a decoherence free subspace. And so for like the photon number super selection rule, if we just attach like a reference system to like each of our basis vectors, you can ensure that the total photon number is conserved, and you can have coherences between different number states and look at the system of interest. So this also leads us to an interesting debate in quantum optics. There's a debate on whether or not the coherence of a laser is objective or not objective. And this is sort of related to the distinction between an intrinsic property and an extrinsic property. So intrinsic properties are sort of explored by this philosopher, David Blue. It's defined as properties of something that depend only on that thing, whereas extrinsic properties depend on wholly or partly on something else aside of that thing. And so turns out when you look at a system and you look at the coherence of a system, coherence is actually an extrinsic property. It's not an intrinsic one. It depends on how we represent our reference frame. For example, if we have a system and we treat our reference frame externally, so non-quantum coherent, we can have coherences between states in that system. But if we actually internalize that reference frame, treat it quantum mechanically, then tracing out that reference and just looking at the system will give us mixed states. And this is related to whether you treat, the state of a laser as like a coherent state, or you consider the light of the laser and the gain medium of internal to the laser as being entangled with each other, and leading you to assign mixed state to the light. So it turns out that difference doesn't change the results of your experiments, but it's only dependent on whether you treat as an internal reference frame or an external reference frame.
What do you mean by it doesn't change the results of the experiment?
So you can actually, you have two equivalent basic descriptions. Or like the experiment, treating one as with coherences and one without. It actually repeats, it actually, gives the same.
As long as you're not changing your reference frame like mid-experiment,
Yeah,
then hopefully you can be consistent with yourself, I guess, right?
yeah, and this is actually like, if you want to learn more, it's all laid out in this source.
Just to, I think elaborate maybe Shravan's question, I'm confused. So what if you measure both of these, in, let's say, the X direction? You get plus the other, in that case, you get a half. With a half probability, you get up or down in the X direction.
I think what will change is what you call as measurement of X. Like, because you're changing the system itself is different, right? So when you say you're measuring X on that size, that might not be the same thing as measuring X on the right hand side.
So, yeah, you would have to do a joint measurement of the reference and the system.
But I have to go back and say this. So at the end of the day, you're only doing a measurement on the light. We're not saying that we're not doing any measurement simultaneously on the gain. And we can ask, with some probability, we see certain outcome. And if one of these states predicts that a certain outcome has probability 0, but another thing says, no, there's some probability. So as Wilson was saying here, the probability of seeing, say, down along X is 0. We'll never see that. Whereas in the other case, it seems like we could see that. It might happen. So there has to be something in that. These two states make different predictions, right? There are some measurement outcomes that can happen in one description that are impossible in the other description. So there's something about this statement. But I remember this debate. I was alive at that time and cognizant. And there is a way, I remember especially Klaus Momer was saying, really argued that, that coherence is a convenient fiction. But particularly between the number states in a photon, whether you really have a superposition of 0 and 1 photons, but anyway, time is short, but
Yeah, so
Negative, actually.
yeah. But
yeah,
it's worth revisiting that question.
maybe
It's not so obvious by just these two statements that, oh, they're actually the same.
yeah, maybe I didn't do it justice, but it's all laid out by,
Just read it.
yeah, just read this paper. It's pretty interesting. And then finally, we come to aligning reference frames. So if we treat quantum systems as being able to store reference frame information, this is the task of what reference frame states and measurements are optimal for aligning reference frames with each other. This is, as mentioned previously, related to calibration and phase estimation. An example is, aligning the direction of a spin, and you encode your reference frame. 2 spins, what is the optimal state? Turns out it's anti-parallel spins, entangled parallel spins aligned along the direction of the reference frame. And that gives you like a certain probability of success. And you can think of this problem in general, you think of scaling the size of your spins. Turns out you're able to have 100% probability of success if you have different spins, but turns out aligning reference frames in the presence of noise is equivalent to covariant error correction. Because you want, if you have like a collection of subsystems, which are supposed to represent the transformation of like one subsystem, then the code should be like covariant with respect to those like transformations. So there are actually like no-go theorems against this, which is related to the decent theory. Because if you think of like these groups of transformations as like possible operations under encoded information, then you know, these restricts the types that covariantly correct. So finite codes can't correct for contiguous transformations. So you actually need like a code to correct for like contiguous transformations perfectly. And you can approximately, you know, you can approximately do this by just like scaling up the size of the code. And there's also this like interesting result where if you have like an ideal clock, like an infinite precision clock, then you're actually able to like circumvent these and able to like perfectly error correct, like, or you're able to like perfectly do transversal gates on any code if you just like attach like a clock reference to that code. But this requires infinite energy. You have like infinite time precision. That way. So you can only approximate that.
Wait, what do you do with the clock? How does that let you do transversal gates?
So it's like similar to this sort of thing, like so your logical zero you attach to, or like any particular transformation you apply on the system, attach a reference state that has like some representation of that transformation. So you're able to like measure the reference state, like reconstruct what operation happened. I guess logical. There's more details buried in there. I wasn't planning on covering it, but it's sort of similar to like encoding subspace. Okay, yeah. So in conclusion, reference frames are essential for understanding application, interpretation of physics theories. So without frame information, you don't have non-trivial interpretations of theory. This is true classical physics as well. And I want to make the claim that all quantum states have extrinsic properties. So they're always defined with reference to something external to them, like whether that's like a measuring device, whether that's like a belief about how these like systems are like partitioned, or something along those lines, or beliefs of observing. And reference frames limit operation tasks. So this lack of reference frame, superselection rules, and these rules can be circumvented by like an appropriate large reference system. And this is useful for understanding basic
No questions for you. I don't want to go like to 5:30. Well,